A lot of this information, I don't know if you could, if it's very easy to pull out of the articles or not. So there's just a lot of ideas and concepts here that I'm really just wrapping up GC. And some things that I'm not so sure we're well covered, but I think are important. So just do your best when I ask you, Pablo. What do you think is meant by linear velocity of a carrier gas? What's the carrier gas? What is meant by the carrier gas in the first place?
The gas that's used.
Yeah, it's called the what phase? The mobile phase, right? They also call it carrier gas. But what do you think is meant by linear velocity? Yeah, it's flow rate essentially, right? Okay. How fast, literally meters per second or something. Okay. Different carrier gases, Kathleen, operate most efficiently at different. There's a reason. Let's jump back up to this guy. There's a reason to talk about this, because in industry or research, or it doesn't really matter what it is, time is money. So that's why we're talking about linear velocity. And why would it be that some gases why would different gases flow at different speeds? Ask it this first. There's an assumption here. If I shot two gases through the same tube, would they both flow through at the same speed? Back up. If I shot two liquids through a tube, would they both flow through at the same speed? Why not? What word would you apply to it? Viscosity. Exactly. We think of that viscosity with liquids all the time. It's so easy to visualize. But does a gas, Adriana, have a viscosity? It does. They most definitely do. So if they have a viscosity, that means there's optimum flow rates. Well, we're not supposed to say that word. We're supposed to call it linear velocity, right? Okay, so different carrier, let's ask Adriana one more time here. Different carrier gases operate most efficiently at different linear velocities. So you would want to pick the carrier gas, Emily, that would have the, since time is money, the highest or the lowest linear velocity. What type of carrier gas would you prefer? You're running the lab, you have your budget. Yeah, faster, right? High linear velocities. Okay? And the story is the gas that this planet is running out of is helium, and that's awesome. That one is awesome for linear velocity. But next best choice is hydrogen. So that's what we had to switch over to. You've seen the gas cylinder tanks. Now that gas cylinder tank of hydrogen costs around, I'd say, $350. And John, it's called 5-9er gas. 99.999% pure. And they call it 5-9er gas, hydrogen. Costs, what I say, around $350, $400. About a couple years ago, we were using helium just like the rest of all the folks running GC on this planet. We had to switch over to hydrogen. Guess, how much do you think that tank of helium would cost us today? Around triple. Yeah, well over $1,000. Sandy, what is it about GC that I need 5-9er gas? Sandy, what the heck? Why does it need to be so pure? It's the mobile phase, yeah. But look, if you're using the what detector, you don't even care what gases are there. FID. But something's going on. It's you have 30 meters of this stuff, 30 to 60 meters. It's the column. right? It's really reactive with what gas? Anybody know? Oxygen. So not only is it 5-9er gas, but you've got this, I don't know if you look closely behind or beside the GC, there's this big cylinder, right? Stainless steel cylinder. It's about the thickness of my arm here, about that long too. And all the carrier gas flows through there. It's an absorbent to get rid of even more what? Gas. Oxygen. Just try to sweep it out of there. Pretty much because if you can pretty much, I don't know if it's good. I think it's okay because I've had it before, air. You get air in the column, it's fine as long as it's at a really low or really high temperature. What would you guess? What's your feeling? At high, everything is more what? Reactive. So really low, right? And for our GC labs, everything is kept at the same temperature simply because you do run after run after run, and I got to get you out of there in an hour and a half, 2 hours, whatever the time is, right? So that's why we're not doing gradients, but very often temperatures are much higher than that. And so anyway, that's the story. Is hydrogen safe to use, Urandi, as a carrier gas? Yeah, we're using it, right? But why am I asking the question, Alice? Why am I asking the question? No. So that if, I don't know, life happens, Alice has to drop out and join the fire department people in San Antonio. She gets called to 4th floor Mets. She knows there's hydrogen tanks up there. Should she be worried?
Yes.
If there's a fire, yes.
If there's a crack in
Hydrogen is it's a rocket fuel. You just have to have what other gas there? Oxygen. And I think we have 20-some% of it around us, so that's a problem. How about number 4?
How do you use hydrogen gas with
Everything's well controlled, right?
Okay.
Because remember, you only have that explosion is well controlled, right? So it's really no big deal, and the carrier gas becomes part of the fuel, so it's fine.
Yes.
For which one?
Under the supervision of...
Well, it has to be safe, otherwise, we couldn't be using it. But I'm just saying, it has the potential to be very, very unsafe.
There's government regulation that we found a loophole for.
And there's this little bottle. It costs about $20, and there's so many things upstairs that really you should be a part of, but I just don't have time. Changing columns, fixing this, changing the gas cylinder, changing the hydrogen cylinder. First they're reverse threads for safety reason. What does reverse threads mean?
Lefty not loosey, righty not righty.
Yeah, exactly. You hear them? And then another thing that I do is you don't have any choice but the reverse threads. But after I hook everything up, I snoop it. All that is I squirt every single connection and look for little bubbles. And snoop is just soap water. That's all I use. It's just soap water, but it's a fancy. Everyone sells stuff, right? And some guy making easy money here, but you just look for bubbles because it's a big deal, and that's the real problem for the darn firemen. I think you go in there. What if there's a small leak? I'm not talking about cylinders, having a leak. That's going to be, that gas is gone in no time, right? Whether it's explosion or shooting through the wall, it's that slow leak that's a problem. Okay. How about number 4, Anna? At least how many analyte molecules must exist in the vapor phase at the designated pressure and temperature of the inlet?
1.
At least 1. All right. Otherwise, non-volatile residue problem will be left behind in the all this is happening in the
Technically, that's right. They are
Yeah.
all
no.
inlet.
I guess the inlet kind of is in the oven. right? Loophole. Right? This is all happening in the inlet. 99% of all your problems are happening in the inlet. Ricky, what the heck was gas liquid chromatography?
That sucks, right? Let's see. Recall what is gas liquid chromatography? Oh, that's when the gas is a mobile phase and the liquid is a stationary phase.
Yes. Where is this liquid?
It's fixed onto the walls of the column.
Yes, that's gas liquid chromatography, right? Perfect word, immobilized.
It's my arteries.
Yeah. Except cholesterol. Okay. Kathleen, what is headspace when referring to a liquid? What is headspace when referring to a liquid? Anybody know what that's referring to? Headspace. Mm-mm. It's a spot where you can sample stuff. I make this nice and tight sealed container here. Here's my liquid. Headspace is right here. Right? Just the airspace, the gas above the liquid. And you're not going to have much of a headspace if you don't seal it. So headspace is where we analyze a lot of things. If you don't want to inject this stuff, right, the liquid, just sample the headspace. And if you have some extra money, you should be. I don't have any extra money. I don't have any money. The wife has everything. She controls everything. Put it that way. Supelco has this measurement tool out called solid phase microextraction. If you have some money, you want to buy some stocks, put it in Supelco. Because what's going on here is I think the EPA, all these agencies are going to be jumping on this patent. Because what it is they have little fibers, and we've done several research projects using these little fibers. All they do is they just sample the headspace. So it's solvent-less extraction. Solvent-less extraction.
What is the software again?
Solid phase microextraction. But the point is that it's extremely, extremely sensitive. And there are all these different ways to kick your analytes out of here and get it into the headspace. And it's really powerful. But, you know, it's slow to catch on simply because, and I experienced this once. I was working for Koch, K-O-C-H. They have a bad rep. They're really not a very environmentally friendly. Anyway, let me just refer to the oil guys. All right, it's kind of like an old guys club, but what I mean is the way of doing things. For the summer, what we did is if you purchase, they want to know how much they should offer or auction off for this barrel of oil. Right? Because it's, they still samples are sent out and we analyze them and they see the quality. We'll see the quality of it, report that, and then they're gonna auction off. This is Arab oil, whatever, coming from wherever. So we have to analyze it, and they want to see how much they should offer for it. Because the real money is in the jet fuels and all that. So see what are the components of this oil. Okay, now these guys have been looking at these reports for years, and you have to do these really old analyses. You put some stuff, do all these chemical reactions, you get a little color, and then you report that color. And that might refer to the amount of, I don't know, cadmium or copper or something, right? It's very, very old style. We had, in the next room that I was doing, I had this table full of all those things that I had to measure just for that one test, just color, and then I had to do, same really old type of stuff. Right across the hallway, we had an ICP-MS. We could have taken this sample, simultaneously measured everything, all these metals that I was analyzing at the same time. But the old guys don't understand that. Kind of a long story, right? But that's why SPME is hung up right now, I think, in my opinion, is the old guys just don't understand it, right? Even though it'd be much more environmentally friendly, much quicker, the whole gambit. Anyway, the mobile phase in gas chromatography is often referred to as the carrier gas because it sweeps away the analyte molecules present in the headspace and carries the molecules down the Robert, down the column, right? Until they diffuse again into the stationary phase. Just a repetitive process. In gas chromatography, all analytes spend the same amount of time in the, Adriana? Mobile phase. As the temperatures increase in gas liquid chromatography, Emily, more molecules move into the temperatures increased. There's always this equilibrium going on between the stationary phase and the mobile phase. And then the mobile phase are shooting through the column. So you crank up the temperature of this whole thing. Would more stuff exist in the vapor phase, or would more stuff exist, the head space? That's where it is. It's a vapor phase, but it's in the head space because it's above a liquid, right? We're doing gas-liquid chromatography. It's above the liquid. Or if you increase the temperature, would something exist? Would it become more soluble in the liquid phase? Here's a hint. All right. Highest energy state is gas. Give things more energy, they're going to turn into a gas, right? So that means that this stuff is going to exist more and more in the headspace, right? More and more in the headspace. No, totally wrong, not column. And in turn, these molecules will elute faster because they're in the mobile phase, right? Okay. Below are two cross-sections of gas-liquid chromatography capillary columns. Okay, let's make sure we can recognize the parts of these things. John, what is this thing? What is this stuff? They're supposed to be capillary columns. What is this big white block supposed to be representing? Anybody see it? It's supposed to be a cross-section. Yeah, the whole thing is a column. So what component of the column?
The stationary phase. The analyte's moving on and off the stationary phase, right?
I'm talking...
You're talking about that white, the
I'm-
arrow thing?
I'm talking about this stuff. If I could shade it all in.
The wall of the column?
Which is what? Glass. That's the glass, right? In fact, what I should have this outside part be really dark. Because what is that? The polyimide coating. Okay? So we've got our polyimide coating. All right? And then we've got the purple would be the glass. Right? And then the very inside layer, Rob, would be what? Stationary phase. Right? Okay, so there's our cross-section. So now let's see if we can answer some questions about this. So both of these columns, A and B, contain the same analytes. There's just one type of compound. And the analytes indicated by the dots, so they're the molecules. In which column does it look like, A or B, will the analyte elute faster? You, Andy, what would you say? Why? Yeah, most are in the mobile phase. They have to. Right? It's the only way to move through the column. Exactly. Ellis, since the analyte is the same in each column, and it's the same type of column in the same stationary phase, same diameter, same everything, what possibly could give rise to the difference occurring in the two columns? That's it. Right?
That's literally
Did you hear what she said? That's it. Now, that's the only possibility, really. Right? Temperature. And remember, that's what you have to control, and that's how you do chromatography in GC, is adjust that temperature. Okay. 3. Anna, in order for the analyte to move through the column, the temperature of the column must be the boiling point of the analyte. Above? Everybody agree?
well, if you have a little bit of liquid in there.
I taught with a person who had totally misunderstood this, and I had to take the person upstairs to the GC and prove it to him, right? That it doesn't matter because of what? Who said? Who picked this answer? Oh, only one analyte molecule needs to be in the vapor phase. If you're a pure liquid, you're in the liquid phase. Do you have anything in the vapor phase? Yes, it's called what? Vapor pressure. Does every single liquid on the planet have a vapor pressure?
Yes.
Yeah.
Giant tablespoon decon.
Yeah, so I mean, you bet. Okay. So let's see here. For a gas-liquid chromatography elution, a single analyte is injected at a temperature well above its boiling point. So it's injected at a temperature well above its boiling point. Is that important? Yeah, it's very different than doing the elution itself within the column. You got to get the thing vaporized to get it onto the column, right? You don't want to be sitting there all day waiting for that. The oven containing the column is operated at a gradient, initially well below the boiling point of the analyte, but reaching a temperature well above before the analyte elutes. So here's the beginning of the column, the middle, and the end of the column. Sketch the distribution of the analyte molecules at the beginning, middle, and end for this elution. Okay, so you have some dots. Go ahead and put them in there where you think. I will ask somebody what the heck you just did.
These look good.
What you think they're going to look like at the beginning, middle, and end. Okay. Ricky, come on up here, dude. Make little dots.
Try.
Show us what you did.
You're gonna have to erase it. Where am I drawing?
I can erase. Just put little dots. Just pretend it's a piece of paper and make little dots what you did.
Thing.
Let's see.
Thing on the
So
thing.
initially, it's
Just do what you think, and we can always have Alice fix it.
some,
Yeah.
and I guess they condense. I don't know.
That's okay. Just do what you think. Put something, and then that's your beginning.
How do you erase this?
Oh, you have to use the other
The
end.
other end? Oh,
Yeah.
Okay. Oh, that's terrible. That doesn't
I
even
guess you
work.
can't erase. So it's permanent. It's in there forever.
I'm gonna go with like in the beginning there's a crap load in the mobile phase, and then like they start kind of condensing and interacting with the stationary phase here, and then towards the end.
It's all right. Thank you, sir.
I have
All
no
right.
clue.
We got a starting point. We have a starting point. Okay. Did your beginning look like Ricky's beginning?
Kind of.
Kind of?
I have stuff in the mobile phase.
You have stuff in the mobile phase? Now, he's got most of his stuff in the mobile phase.
That's what I have. That's my stuff.
You have most of your stuff in the mobile phase?
All my stuff. All my eggs are in my basket.
Okay. And then in the middle?
I have crap on the stationary.
Now, let's back up a little bit, though. Does this first one make sense? The temperature is well below the boiling point, right?
So they should all condense onto the stationary phase?
I'm not sure if condense is the right word. It might be the right word.
Okay.
Because condense kinds of means something hot turning into a solid or liquid on something cold. So that's not what's going on. What's going on is an actual dissolving, an actual solubility, like dissolves like thing going on. It's like taking a solution and taking some water, putting a drop of ethanol in there, right? Getting it to mix up, and then take a whiff of it. So you can smell the ethanol. Your nose is almost just as sensitive as that dang FID. It's really sensitive, so it really works well. Okay, so then you heat up the water. Take a whiff of it. Would you smell more ethanol?
If you heated it, yeah.
If you heated it, you dang right you would, right? Because remember, you're kicking everything into the headspace. There's more energy, right? In fact, if you
I haven't either.
remember when do things boil? Yeah, so as you heat things up, the vapor pressure keeps going up. And it keeps going up. You heat it some more, things keep going up. So that means more and more stuff is going into that vapor phase. It doesn't matter if it's water, ethanol, everything will, right? Okay, so at the very beginning, right? Yeah, a lot of years and years of practice. All right, at the very beginning. The point of what I think confused you, what got you, was that well above the boiling point in the inlet. That's just the inlet. Remember, these are gases. Man, if you put a drop of ethanol in the hallway, you'd smell it here in pretty much no time. Gases diffuse extremely quickly. And diffuse is probably the word would work. It works better than condensation. These gases diffuse into the stationary phase. All right? Okay, so then things are warming up. Now it's pretty much a gradual change, right? Things are getting hotter, and then they're getting hottest. So you just make sure you have proportionally more and more in the what phase? Mobile phase, as you go along here.
It's just the way it's worded.
Something like that. Just have more and more in the vapor phase. And the head space is the word we're supposed to use, right? In the head space. Because it's a space above a liquid. Different peaks have different sharpness in GC chromatograms. In other words, some are narrow while others are wide. The peak shape is decided on what the analyte is doing at the, Kathleen, end of the column. It's an important point to remember, at the end of the column. Because that's where your detector is, right? Right at the very end. With the cross-section of a gas-liquid chromatogram, I don't think you have this, you just have to add it, right? Because I added it this morning. Use dots to illustrate the distribution of analyte molecules that would result in a very sharp peak in the resulting chromatogram. So this is both the end. So in A, this is the end of the column, right? But you want what distribution would give, very fat or very narrow? Very sharp. So this will give a very sharp distribution. And then in B, again, the end of the column, but you get this wide peak, right? Sharp, wide. Put in what you think it would look like. Okay, Adriana, come on up. And let's see what you did. Yeah, I'll do them both, whatever you think it's going to look like. This is the very sharp distribution of the molecules, and then the very wide. Okay. All right. Good. Now let's just make these touch, though, right?
Yes.
All right. So, which one, John, which one of these distributions are we pretty much getting, do you think, when we do our GC labs? John, have you done the? Okay. Remember your pentanol peak especially is a good hint. So are you getting extremely, that you can't even see the baseline? That is a GC peak. This is more like liquid chromatography or something. But didn't we get a lot of these? We got a lot of fat peaks. We didn't get a lot of this stuff. The reason, you have to zoom in, right? If you just look out and let the thing handle its own window size, then yeah, it might look like that one. But you need to zoom up and see the differences. Okay, zoom up and see the differences. And when you're doing GC, the solvent peak, you never let the solvent peak control your window size. You should always draw a box around it so then you can see the other peaks, right? So that solvent peak should always be cut off when you're illustrating a chromatogram. All right, good. Can too much sample be injected on a column? In other words, do capillary columns have a capacity, Sandy? Yeah. There's only so much space. Look at the dots we're drawing. Right? There's only so much space to interact with that stationary phase. Which, if any, has a higher capacity? Randy, a small or large diameter GC column? Which one would have a higher capacity? Could handle more analyte. The larger one? Why? Yeah, more, what's the technical word? More surface area. More surface area, right? Alice, do you think liquid chromatography columns also have a capacity? Yeah, sure, why not? Okay. All right, our last one. And you've got 3 minutes to figure this out. One way to have compounds elute faster is to increase the pressure in the column. Right? Because remember, time is money. So get that stuff out of there. Why is a high pressure a bad thing to have, especially in the inlet of a GC? So the question really is, this really gets to the point, and let's just focus on this part. Why is a high pressure a bad thing to have in the inlet of a GC? Think about it. Degrading your septum thing?
It's a green thing.
The rubber septum?
Because when we're talking about how that's always releasing.
Yeah. But we've got the what purge?
The septum purge.
Yeah. But why would it degrade at a higher temperature?
Just what things do at higher temperature.
No, not higher temperature, higher pressure.
Oh, no.
Okay. There's a couple hints here. This is a hint, but it's not that strong, really. This might be a better hint. Might be.
Oh, things boil at a lower temperature. It's under higher pressure.
No, at a higher temperature. So like the analytes won't be able to vaporize, is that why? Because the analytes won't be able to vaporize when the pressure is too high?
No, they still vaporize
They
at a higher
vaporize
pressure. They should
easier.
vaporize quicker.
Because like at higher altitudes, things boil at a lower temperature because there's not as much pressure on them. So that's what I'm saying.
He's on to something, but he hasn't finished the story.
Finish it.
I
I
don't
didn't say the end.
I don't even know what it is.
He's right. You crank up the pressure, things boil at a
Lower temperature.
Higher pressure, higher temperature.
Y. And that's just before we finish the story. Let's make sure you understand that point.
The atmospheric pressure is pushing down on it, so the vapor pressure, it has a harder time pushing its molecules into the gas phase.
Yeah. Do you hear him? If you increase the pressure in that box, right? He's exactly right. The solvent molecules are going to have a harder time to getting out of there.
I know.
Right?
That's,
So you have to crank up the temperature to get that dang thing to boil, right? The vapor pressure has to be even higher.
this is like
Actual
exactly
hell
opposite
does-
from organic.
We'll talk about that in a little bit, okay? Okay, so does that make sense? You crank up the pressure, right? Things boil at a higher temperature. Because things boil when the vapor pressure finally reaches the external pressure. That's when things boil. The whole liquid turns into a vapor. It's not just the top part, the whole liquid. Okay, now what is so bad? Now let's finish the story. This is why it's so bad in the inlet of a GC. What is the problem with GC? And remember, it can only do what percent? 20%.
That's too much work for it.
If you crank up the temperature on some stuff, they decompose, right? You don't want to go. You want to go to the minimum temperature you need to go to get that thing to vaporize, right? At its boiling point. So you pretty much want that at the lowest inlet temperature you can get by with, is because 20% of all the compounds in the world is it. That's it. Okay. Now you can go through if you just don't have any choice, you can derivatize, but you got to know your organic chemistry to start messing with things so that the compound, you're actually altering the compound so it won't decompose on you at that temperature. Okay. Okay, what was your question for organic?
Why do we do vacuum distillation? Put something under pressure and it boils out.
Oh, vacuum.
You got it backwards, dude. You're putting it under a vacuum.
Oh, okay.
Vacuum, you're reducing the pressure. So do you have to heat it up as much? No. Mr. Who did the Ramsey Young lab?
They did it.
Yeah, Ramsey.
They did it wrong.
What Ramsey Young?
And P-Chem.